We're all ready to go.
My brother is even in vendor design. I'm just going to call it graphical design. There you go. He's into graphical design and animations. We got 10 years. Yeah. Honestly, animation is why it's important. Like I can do pretty much everything else in the game. He's really good at it too. Don't have it. I can't even enter the walk. Do you know who Kumon was? No, that'd be the student. I'm very kind of drawing cases and stuff. I just can't get them. But like, I can animate a few things, but like, they're really basic. They're really good. I think it's all character position and it looks like good photo. Maybe if you make the character it's any vision. Yeah. It's like a bunch of motions. I think I might be the right song. I think I need like if you look like the character yeah, like I need to see the previous frames. Like the book of waves. I think I need like I'm sure I got some software that I just have to work through. Really helps if you know the safety example of the previous frame, you can tell how we play out. And if you're just using one thing at one time, it's hard to do. That's the how I started. I might be able to like maybe you know look at animation. Animation would make me game. I'm sure that's real. Well, it's not entirely. Motion, animation is not. There's a lot of other stuff like that. And slow getting stuff. Animation is actually a little bit, but animation is really fast. No, but really, yeah, it really helps. Makes that maybe with great camera angle and great soundtrack. We've got great and I don't know. I was just thinking about like 30 versus. Oh yeah, I am. But also 2D because then you have the yeah, there's also a lot of games that don't have to be a lot of that. It's not like at work, it's not usually one thing that makes or breaks the game. You can kind of do without most of the concept, but you have to be good like other concepts. But it will be a
Well, we got another 40 seconds. So if you guys have any questions, we can try to make use of these 40 seconds. Yep.
Much longer until the lecture starts.
Another 30 seconds.
To be or not to be, that is my question.
I think these days it's to chat or not to chat. I was watching a video to argue that Chat GPT AI or anything that runs on computers cannot possibly have understanding of words the way we do. And I spotted a lot of perspective issues with that claim. So it's an interesting video. I can show you guys when I have time. All right, so it is 5:30. I'm getting started. All right, so a few things just remind people. PowerShell is installed on all the computers in STEM 301. So that means, if you want to get, River Spider to work, you can do so, okay? You can actually get it to work in the lab. The best thing to do is to basically take the entire zip file, put it onto a folder on a thumb drive, okay? Then you can configure everything that you need to configure within that folder. When you go to the lab, you plug in your thumb drive and you do everything from your thumb drive. So this way, just remember to take your thumb drive home when you're all done. Other than that, that would be the best plan, okay, if you want to use River Spider, because I think it can really help not only to speed up the homework assignment, but also to get you another level to gain understanding of the concepts that we talk about in this class. So once again, it is optional. So this is what we're going to do today in this class. And there's a program here called post. Huh? How big is the file? You mean River Spider? I do not know. It's a zip file. It's not that big. So if you have anything that has at least, I'm going to say, a few hundreds of megabytes, that should be fine. Yep. All right, so this is what we're going to work on today, which is called postinc.c. We are going to take a look at the C program first. I'm hoping that some of you have the time to kind of preview it before class so that you have an understanding of the C code itself. If not, that's okay. We are going to go through the program ourselves at this point, but it's not going to be, I'm not going to get into a lot of details of tracking this program. This is the entirety of the program, okay? It's not that long. So we have main. Main has two local variables, x and y. X is initialized to 2. Then we call postinc with the address of x, and then whatever postinc returns, we store that to y. And the entire definition of postinc is up there from line 3 to line 9. So the question is, what does it do? In other words, by the time we are done with line 15, what is the value in x and what is the value in y? That is the question. What do you think? Well, first of all, am I using only the features that you have been introduced in CISP310? Because I want to make sure that I'm not including any feature that in C or C++ that you guys have not been exposed to. Which line? Line 7?
And then no 15. And then
Line 15. Ampersand x. This one?
yeah,
It's an operator that says address of. So ampersand x is the address of x. I'm hoping that topic has been covered in CISP360. Yes or no? Yes.
The star, the key bar is like the data and the key bar, right?
It is. So the asterisk is dereference, which means you'll treat whatever is immediately to the right-hand side of the asterisk as an address, and then go to the location. And the location is what we are interested here. We are incrementing the value at the location the p-var is quote unquote pointing to. This is basically passing by reference the old school way.
So pre is given the address like key bar.
Sorry? So pre gets the value of whatever p-var points to before the increment. What was the question?
Because I remember one where it's, when you increment the value, there's like a copy of the value and you don't actually increment the value itself.
That's only if it's a non-reference variable. Because you're creating a new variable.
So this is plain C, okay? Plain C has no pass by reference. So this is the closest we can get in regular C in order to implement passing by reference. So do you guys still remember what is pass by reference? Sort of. That is not good enough. I'm afraid that is not good enough. Yes,
Fast by the, like, the memory location.
especially for big things, okay, but also for things that you want the subroutine to change. So it looks like I probably should run this program through the debugger and show you guys a few things. Just so that we have an understanding of, what each thing is doing. So that's what we'll do. Okay, not a problem. Not exactly what I had planned, but it's okay. That's what makes the classes interesting, is to do things that are not planned. If everything is as planned, life would be very boring.
Nice though.
So the question is, would you rather be a train on a track, or would you rather be a dune buggy, doing whatever you want? Exactly. But make sure that you're a dune buggy with a roll bar. Just in case you flip over, you can just kind of write it up and you can go again. Huh? Yeah, the horses cannot go that fast.
Field buggies have like 30 horsepower. Yeah,
All right.
horses not have long.
So we're gonna run the program and find out what it does, okay? So we are going to put a breakpoint on line 14, okay? Because line 14 is the first meaningful line. So we run the program, now we are on line 14. All right, so line 14 is quite easy to understand. X gets 2, okay? That's all it's gonna do.
Yes.
Variable X is updated to a value of 2. So if I single step, okay? And then I print X, X has a value of 2, no big deal. But there's one more thing I want to do. Where is X? Okay, so I'm going to ask, where is X? So this hexadecimal number here, 7, a bunch of F's, D, F, C, E, that is the address of X in memory. Now, why doesn't it look like, the memory addresses that we see in TTP? Because this has a 64-bit address as opposed to 8-bit in TTP. So the TTP has a very tiny amount of memory, and yet we're going to do a lot of fun stuff in TTP. But the point is, this is the location, and at the location, we have a value of 2. The reason why you see quote, or double quote, \002 is because an unsigned 8-bit integer is also known as a char, an unsigned char. So as an unsigned char, the debugger is trying to be smart and say, hey, as an unsigned char, this is the character that is represented by 2 in ASCII, which is nothing special. Okay, so then you ask, but why do we have 002? Because it is a convention that when we print a character by its ASCII code, it is an octal number. It is a base 8 number. So that's why it appears as quote \002. The backslash is escape, which means okay, the following is the ASCII code in octal, and then the 002 is the octal number corresponding to 2. All right, so nothing too mysterious here. So we're going to single step. Actually, yes, we're going to single step into the subroutine. So we are now on line 6 of the subroutine, which is pre gets whatever p bar points to. So the first thing we want to know is what is exactly p bar as our parameter? Well, the parameter is the address of X. So it is not the value of X, it is the address of X. Okay, so by passing the address of X to the subroutine, now the subroutine has access. It knows where to find a local variable that does not belong to the subroutine. Okay. All right, so we single step, and then we ask, oh, so exactly what did we store in pre? What do you guys think? If I press the enter key right now, what is in the local variable pre of host name? That's 2, exactly. Okay, so we'll double check, make sure that is the case. Yep, it is 2. Nothing exciting, right? So we are ready to execute line 7. So now the question is, what does line 7 actually mean? What are we incrementing? Because plus equal to 1 means we're adding 1 to something. So are we adding 1 to the pointer, or are we adding 1 to what the pointer is pointing to? It's adding one to where the pointer points to. Now, in this case, I technically do not need a pair of parentheses, but I'm adding those just to emphasize that the entire left-hand side refers to what the pointer P bar is pointing to and not the pointer itself. Is that okay? All right. So we single step again. And then we try to print pre again. So pre has not changed because pre is a snapshot of the previous value that P var is pointing to. It's a snapshot. It is a copy. It's a duplicate. Okay. But what is interesting now is if I go print whatever P var points to, it should be 3, right? So we can do that. We can say print whatever P var is pointing to. It is indeed 3. Some of you are going to say, so did we just increment the local variable of main, which has an entirely different scope, so that the subroutine cannot see? The answer is yes. The next question is, Tag, you can claim whatever you want. Can you prove that? So I can prove that. Okay. Now this is something that is actually useful when you debug a C or C++ program. The tool is called backtrack or backtrace BT. The first thing we need to do is, BT is what we need first. So BT is showing you all the invocations of subroutine up to this point. So it's showing you that we started in main is calling post-inc, and we are currently on line 8 of post-inc, the function. Is that okay? But it is also giving you the frame numbers. Frame 0 is always referring to the current frame, okay? Exactly where the execution is right now. Frame 1 is the one before. If there's a frame 2, it is the one before that. If there's a frame 3, it is the one before that. In other words, by using BT or backtrace, you can know how you get to a particular function, the entire history. Who is calling who is calling who is calling who in order to get to where we are. Is that okay? If you are defining if you're writing a subroutine that is recursive, this is one of the best tools that you can use to debug that type of function, because it can show you that the function called itself, but it will also show you that every time it called itself, how the parameters change. Without doing any extra work, it will basically show all the invocations, of the same function, and it will show you the values of all the parameters. In this class, we will deal with recursion at some point, just not now. Okay, so when we get there, we'll also use that feature. Another command in GDB that is also helpful is called frame. In other words, this is allowing us to change the current frame, which is by default where we are in terms of execution, to a previous frame, the caller of the current subroutine that we're in. Is that okay? So by saying frame 1, I'm switching the frame of reference back to main. So press the enter key. So now if I ask, show me what is P var, because P var is the name of a parameter in post-inc, it's going to say, I don't know what you're talking about, because it is seeing things from the main subroutine's perspective. There are no P var in main. But we can ask, what is X? So now we can say, what is X? This X is referring to the local variable of main, because we are now, our frame of reference is now back to main. So we can actually ask, what is X? It is indeed 3. So I have just proven to you that the pointer called BP bar in post-inc is basically a pointer, otherwise known as the address of local variable X of main. Is that okay? So now we can continue the execution of the program. And I would go back to frame 0 to continue execution. It's a simple return statement. So it's only returning pre, which we know is 2 already. So the return value of post-inc is 2, which is the value of the location that P var points to prior to the increment. And that's why it's called post increment, because the increment is happening before we extract the value that P bar is pointing to. So now we single step, and we're all done with post inc, and we're now getting back to main. It is also done with the main subroutine, but now we can also print what is the value of X. What do you think is the value of X? We just saw it earlier. It's a 3. And what about the value of Y? Y is 2, exactly. All right, so we know the effect of this code. We understand the concepts, the address of, passive parameters, local variables, and so on, at least from the perspective of a C program. Now we're going to switch around and say, can we write this code in assembly code? Now, I'm only using TTP in my class, but obviously it can also be done in any architecture because the concepts are the same regardless of the architecture. So are there any questions before I get out of GDB? Yep.
So frame, let's say back to frame of reference and BT
Backtrace.
backtraces to the previous step.
No, it shows the entire path of how we got to the function where the breakpoint is, which is going to be super helpful when you write recursive subroutines. Okay, I'm just curious if you're in 430 or if you have taken 430 already. Did you guys learn how to use backtrace? Did the instructor teach you how to use a debugger, backtrace, and all that stuff? No. So how did you debug your recursive functions?
Yeah, this is pretty much been do it. And then you
Because-
just says, go figure it out.
I see. Yeah, because backtrace would have been super helpful because you can put a breakpoint in those functions and then do a backtrace. Then you know, oh, this is calling this. It's the same function calling itself, but you also can see how the parameters are changing, and you can also change the frame back to an earlier point and go like, am I supposed to do a recursive call because I think we have reached the basis, or the base case, and we should not have, called ourselves recursively anymore. So you can check all of those things here with backtrace. All right, so now we are gonna continue, and this time we're gonna write the assembly code corresponding to the C code. So we'll do a VM, I think it's an uppercase O because I want to split the screen to show the C code on one side and then the assembly code on the other side. It's called postinc.c on one side, postinc.tttpasm on the other side. There we go. All right. So this time when I write this program, I'm going to treat main as if it is just a normal function. In other words, the initialization of the stack pointer will be done at the entry point, like on line 2, I'm going to initialize the stack pointer, and then I'm going to call main as if it is just a regular function, and then the halt will be right after that. So it's better for me to show you exactly what I mean. No up here, and then we have LDIA with return 0.1, and then we have a decrement D, STDA. So that's pushing the return address, and then we call main. When it returns, we are going to halt. All right, so right here, I'm going to give you guys a few recommendations. Is when you, oh, I forgot to define the label. So let me define the label first. Okay, that's a good, okay. I'll just say that I did not forget to define the label. I intended this as a question to you guys. Where should I define the label ret1, return 1? Between which 2 lines?
Between 5 and 6.
Between line 5 and 6. That is correct, because we want the return address to be the address of the halt instruction. When main comes back, when main is all done and say, I'm ready to go back to the caller, what should we do? Nothing. There's nothing left to do except to halt. Yes.
If you put it after the halt line and then put another halt line, it wouldn't affect.
That will still work. Yep. But you would be wasting that halt that is immediately after the JMPI. because nothing can execute right after the JMPI unless you branch back to that point. All right, so that's all good. And we are going to look at which one do we want to implement first? Your choice. Main, okay, so we can do main. All right, so here's main, and I know main has to return. And so I'm just going to write in the code to return right away, which is LD, DD, increment D, and then JMPD. All right, so at this point, I want to show you, at this point, how you want to look at this program. Instead of looking at this program really instruction by instruction, you should start to recognize templates or patterns. What kind of pattern are we talking about? The push pattern, the pop pattern, the return pattern, the call pattern. Okay, so from line 2 to line 6, it's a call pattern, which includes a push pattern inside it. From line 10 to line 12 is the return pattern, which has a pop pattern built into it. The pop pattern is line 10 and line 11. The push pattern is, I'm just going to say line 3 and line 10. Are we doing okay so far? Now, this is all being recorded, okay? So you don't have to frantically write down what I just said, but it is important to remember what I said, in general, which is, it is important to recognize the template, the pattern, and not really just to look at the instructions by themselves. Because if you look at instructions by themselves, it's not going to be, it will take a long time to understand what a program is doing. But if you look at a pattern, then you recognize, oh, this is just push, this is just pop, this is call, this is return. It makes it easier for you to interpret a program written in assembly. All right, so now we're going to backfill what main is going to have. So according to this, main has 2 local variables. Right away, we go like, what are we going to do? Where are we going to put all these local variables? On not registers, because we only got 4 registers, they're very precious. If you put it into the registers, we can only have 3 bytes because we only have registers A, B, and C available to us. Register B is a stack pointer, we cannot use it. So that means if you were to use registers, you would have very limited number of local variables, which is not good. Okay, so we're gonna push it on the stack. So this is where things is up to the called subroutine to decide. Local variables has nothing to do with the caller. So the subroutine being called gets to decide how it wants to arrange those local variables on the stack. So I'm going to draw a picture because I know some of you are more visual. So a picture can potentially be helpful. So here is my Zerno screen that you can see. And then here's my Zerno screen that you cannot see, but if I need this one in order to actually draw something. So generally speaking, when you call a subroutine, there are things, right? You can potentially have arguments, okay? So you can potentially have argument 3. I'm just using this as an example. Argument 2, argument 1. And then after you push all the arguments, what do you push? Every single subroutine, when you call a subroutine, you always have to push this on the stack. What is that? Return address. Very good. Okay. So you push all the arguments first, and then you push the return address. And then at that point, the stack pointer will be pointing to the return address, and then you use a JMPI to go to the subroutine. So this is why the convention is by the time the subroutine, at the entry point of a subroutine, the stack pointer always points to the return address. Okay, above that would be optional arguments. Sometimes they're arguments, and sometimes they're no arguments. And where do you think we should put our local variables? This is what the stack looks like at the entry point of a subroutine. So if that subroutine says, I kind of need a few local variables, and I know I'm supposed to put it on the stack, where should we put those local variables? Okay, I cannot hear because there's collision, right? less than, lower than the return address. Okay, very good. So that means, we want to put the local variables somewhere around here, right? Remember the gremlins? They're gonna mess up anything that is below where the stack pointer points to. Do you want the gremlins to mess around with your local variables? Probably not. So how do we reserve that chunk of memory and just go like, don't touch that, okay? Those are our local variables, just don't touch it. You decrement the stack pointer. Exactly. So what we need to do is to move the stack pointer down to wherever you need so that we can have this region of memory reserved for our local variables. Is that okay? So I'm hoping you guys are starting to see the importance of the stack, because everything that we need to store is actually on the stack. We have not talked about global variables, okay? Because we really should not need global variables in most programs. So so we will defer that discussion until much later. So now the question is, within the local variables, if I have two, but main has two local variables, should X be the one with a high address, or should Y be the one with a high address? What do you think? It's a trick question because it doesn't matter. As long as you use those offsets consistently, it doesn't matter. Okay. All right, so is this picture helpful? Okay. I kind of vaguely remember seeing this picture somewhere in my modules. Can someone point to which module has this picture? Yes.
Why do we store them after the return address? Why not store them above it?
Because you have no control over what is above the return address. The return address, okay, which ones are pushed by the caller? Argument 3, argument 2, argument 1, and the return address, those are all pushed by the caller. So the callee, the subroutine that is being called, by the time we get to the callee, the stack pointer is already pointing to the return address. And you're not supposed to mess with things that the caller is pushing on the stack. So you really don't have a choice but to use the locations below where is the return address. Is that making any sense?
Is it because it's a local variable to main?
No, it's local variable to the subroutine being called.
Yeah, but we're in a subroutine. Like,
Main is a subroutine, yes. Main is a subroutine. Yes, you got a question.
I was gonna say it's kind of like a file cabinet.
But it's local to the subroutine being called. Mhm. Yep.
This is inside a.
Okay, so the question was, let me repeat the question. So this is inside the subroutine. The answer is, this is inside what we call a frame of an invocation. Okay, so we'll need to get those terms really clear, okay? What is a frame? What is an invocation? And what is a function? So we'll deal with invocation versus function first, okay? What is a function? Well, I can show you a function right away. Line 3 to line 9 is a function. A function is a description of what needs to be done, how it is done, what is the name of that chunk of code, what does it need, and what is supposed to be returned. That is a function. What is an invocation then? An invocation is it's an instance of calling a subroutine. So if you have something that's recursive and it calls itself like several times, then you have multiple invocations corresponding to the same function. Yes.
So number 15, that's an invocation.
Number 15 is a line of code that causes an invocation. Yes. So what is a frame then? A frame is the data that is needed to track an invocation. Is that okay? All right, because the most important part is to differentiate between a function definition, which is really just describing what to do when the function is called, versus an invocation, which is an instance of actually calling the subroutine, and it calls, the frame to appear. The frame is the data structure behind an invocation. Are we doing okay so far with that? There's only one single function, but you can have multiple invocations corresponding to it, especially if it is recursive. All right, so assuming that is okay, that is good. Now we look at main and go like, what should the stack look like? Okay, so we'll go ahead and take a look at the stack and see it has the return address. And we need two local variables. Now, whether you want Y here and then X over here or the other way around, doesn't really matter, okay? The C++ compiler has no specification of whether the relative locations of your local variables should have anything to do with lexically which one is declared first. Okay, so it's entirely up to you. As long as you use it consistently, it's okay. It is not an agreement between the caller and the callee because local variables is strictly a callee kind of thing. So the caller does not need to know it, and therefore the callee can decide however it wants to do it. Are we still good so far? Okay. But we know that originally the stack pointer is here, pointing to the return address, and we needed to point here, after we allocate for the local variables. So that means we have to change the stack pointer. We have to decrement the stack pointer twice in this case in order to allocate those 2 bytes, one for X and one for Y. Okay. So we'll go ahead and say decrement D, because we need to allocate for the local variables. So allocate for local variables. Okay. All right. So from at this point, if this is how I want the stack to look like, return address is at the highest point, X is the next one, and then Y is at the lowest address of the entire frame. Then I have to remember this in my head all the time, right? Where's Y, where's X, because sometimes I cannot remember how I did the allocation. So this is where you can introduce symbols to help you remember where those things are in terms of an offset from where the stack pointer is pointing to. Okay, you might want to jot down the time because I think you might find it useful to be able to get back to this point of the lecture from time to time. It is 6:03 right now, and I'm going to talk about how to use labels to remember how to get back to things on the frame. Okay, all right. So I'm going to start here, and I'll say Y as a label. Okay, we'll use main, the name of the function as a prefix, and then Y is defined to be 0. What does that mean? Does that mean local variable Y has a value of 0? Nope. What it means is local variable Y can be found at 0 bytes away from where the stack pointer is. In other words, the label is remembering an offset from where the stack pointer points to in order to find a particular thing. In this case, local variable Y of main. Yes.
Is it like a comment only for us, or is it the code users?
Well, this is assembled. This is going to be treated by the assembler, and the assembler understands every time it sees main underscore Y, it is the same thing as a 0. So it is actually code, but it is for our convenience. If you have a really good memory and you know exactly what each thing is on the stack, you don't need this. I don't have that kind of memory, so I need symbolic names. Yes.
So how much of a difference is that in comments?
This is actually used by the assembler. You'll see. So I can say this, right? I can say X is 1 byte from where the stack pointer points to because it is right after X. I can say that. Yes.
What if you later want to add one more variable?
That is a very good question. So that means using a constant of 1 is not a good idea. It is better to say main Y 1 plus. This 1 here, it still needs to be a 1 because this 1 refers to the size of Okay, I need to be here. So this one is referring to the size of y. So where I can find y, add the size of y, and that's where we'll find x. That's what it's saying. So everything is defined relatively, or I can say, what is the other term to say that? Everything is defined in a relative term. I think that's the best way. Are we good so far? What about the return address? I don't need it, okay? Nowhere in the C code says mess around with the return address. So I'm just gonna leave that alone. Are we good so far? Okay. So now the question is, okay, with these label definitions, how are we going to implement line 14? You can sort of, okay, I'm gonna say sort of, you can sort of look at line 13 to line 16 of the assembly code to be doing about the same thing as line 13 in the C code. The declaration of X and Y as local variables. Because I'm both reserving the space and also, giving those locations names so that I can later on use the names to refer to those locations. All right, so we're going to move on to line 14. So line 14 is the first line that says, okay, so how do we get back to the local variables? So typically, when we look at an assignment operator or an assignment expression, it has a left-hand side and a right-hand side. The left-hand side specifies where do we store something, and then the right-hand side specifies what value are we going to store to the left-hand side. Do we have any questions about the basic anatomy of an assignment expression? Questions? Okay, all right. So depending on which side is more complex, we want to perform the more complex side first, okay? Because we want to have as many registers available to us, to perform the more complex side, and then the less complex side is like, okay, we don't need a whole lot of registers to do that. So in this case, we'll do the left-hand side first. Okay, so the left-hand side is just x. So the question is, where am I supposed to find x? Well, we know how to find x. The offset to find local variable x from where the stack pointer points to is main x. Okay, so that means I can use some code like this. LDI main, put it into a register. Let's say A, main x, and then we do a add AD. So can someone tell me what is in register A after line 20 is done? All right, so I know this is a little bit tricky now, okay? Line 19 is loading the offset of where we can find local variable x from where the stack pointer points to into register A. It is nothing but an offset. I think you got it first.
So it should be the address of X
On which one?
after the line point.
Okay, that's one answer. Go ahead.
I was gonna say it's going to be the address of P plus the main tag. The address of where P is
Yep, you're correct. You're both correct. So at this point, after the add AD, A is basically the address of local variable X. And this is how I would denote it, okay? I note that I use double equal and not a single equal, because I want to express that these two things are the same. So I want to make sure that I differentiate that from updating X with the address of X. Are we doing okay so far? Okay, so now we can move on and we can now handle the right-hand side. The right-hand side is easy. All we need is a 2, but we cannot put it into register A. We can put it into, say, register B. So LDI B with a 2, and now we can perform the actual assignment, which is, can someone tell me how to do the assignment? I have the value of the right-hand side. I know where to store, based on the left-hand side. So which single instruction do I use to accomplish the typing? Yes.
Is it ST parentheses A, B?
That is correct. Very good. ST A, B is what we need. There we go. Because A contains the address corresponding to the left-hand side. B contains the value corresponding to the right-hand side of the assignment. Okay, since we got both of those in registers already, store is exactly what we need to complete the operation. Yes,
This entire thing just did line 14.
this entire thing, well, I would say not the entire thing, from line 18 to line 24 is corresponding to line 14. I think you're now starting to understand why the C programming language was developed. Because without the C programming language, the two geniuses or genii who invented Unix was originally planning to write an entire operating system using assembly code. I think they tried it maybe up to the first, maybe 1,000 lines or so, and they go like, no, we are not going to do this. We need a shorthand. That became C. Yep.
So accessing any kind of local variable is basically just getting values that are offset from the stack, but we're never actually moving the stack pointers.
That is correct. Because you don't want to move the stack pointer, because the stack pointer is kind of like a fence. You can look at the stack pointer as an electric fence, keeping the gremlins away from your garden. So you don't want to move that electric fence unless you have to. All right, so that's line 14. Let's go ahead and deal with line 15. Yes.
So is the purpose of doing all of this so that we have a variable that we can collect that has the value in it? Couldn't we just as easily just use store D, or I mean store D and then whatever value we're trying to put into X?
Assuming, the variable. Well, in this case, we cannot, because register D is pointing to where? It's
Right,
pointing to,
yeah, I'm saying-
it's pointing to Y.
After the first step, so we decrement once and then we say.
Yes, you could have done that too. But to do that means your code is dependent on the actual location, which means the moment you try to add a new local variable before or after, then this code may or may not work anymore. So I'm trying to isolate all the changes that I can potentially be making from the existing code that is working already. By using it this way, yes, sometimes it's wasteful, because if this were y equals to 2, then all of these operations is like meaningless, because your main underscore y is just 0. Why would I want to put 0 into register A and then add register D to register A? I could have just said STD something, right? But this kind of coding helps me isolate from changes and other types of things that might happen, and it's pretty quote unquote universal.
And then you don't have to keep track of what everything is.
Exactly. So I'm wasting a little bit of code in order to maintain my sanity, which is important. Yes.
So really the whole purpose of, I guess, arranging your code in this specific manner is to future-proof your application.
Yes.
If it were to change in the future, then it's not as prone to breaking if you were to say.
That is correct. Yeah, that is correct. That's a very good way to explain it. So some of you are kind of more driven by efficiency, and you go like, so are there any ways to look at this code and optimize it? The answer is yes, okay? There are such things called peephole optimizers. Okay, peephole as in the little, thing optic, in the door. So it's called a peephole optimizer. So peephole optimizer can basically look at they can look at a moving window of code, and it will recognize patterns and go like, hey, this pattern can be replaced by this more efficient pattern. So it's a pattern matching kind of thing. It's like, oh, this is doing the same thing as that, but this is more compact. Let's replace this with that. So a peephole optimizer can potentially look at this code and do the optimization. But from our perspective, since I'm manually writing the code, I would much rather waste just a little bit of code to make it so that it is less brittle. Okay. All right, so we are moving on to line 15. So line 15 is a little bit more complex. Can someone tell me what is the thing that I need to do? How many things are there? Okay. First of all, it is an assignment operation, right? The last operation is assignment. But before I can do the assignment, I have to deal with the left-hand side. We don't have to deal with the left-hand side. It's kind of the same thing like the previous one, except this time is y. But the right-hand side gets a little bit complicated this time, right? The right-hand side is a function call. We are calling post-int with an argument. Okay, so in order to call a subroutine with an argument, what do we need to do? Yes. Exactly. So we have to push the argument on the stack, then we quote unquote call the function. Very good. So that would be the first thing we need to do is to push the address of X on the stack. Okay. Very good. I'm just looking at this code here, and I say, if I were a very efficient person, I would not have to do a single thing. I can now just say decrement D STDA. That would have pushed the address of X on the stack. You could go like, what? What? Well, because you have to track what is in the register throughout the execution of the code. By the time we get to line 20, by the time line 20 is done, register A has the address of X. When you look at all the code between line 21 to line 27, did I change the content of register A in any way? No. So register A still had the address of X. Kind of handy. Okay. So I'm just going to take advantage of that and say, oh, my argument is already sitting in register A, just push it on the stack. Okay. And then after that, we have to call the subroutine. So that's a pattern thing now. I'm hoping that by this time, it is now becoming a pattern instead of having to really kind of think about what to do. So I'm going to give you a new pattern. Okay, I know once we establish a pattern, you don't want to change it, but I'm going to give you a new pattern. This one is kind of fun. Okay, you look at this and go like, but that doesn't look like a pattern that we have seen before. And I'm telling you, I did not forget a label definition. This is all I need. So you look at this and go like, okay, how did it get the same thing done that in all the previous examples, including the code that was before line 14, that always use a label to designate where we're supposed to return to. But in this case, you're loading something into register A and pushing it as if it is the return address. Why does A contain the return address? What is this .6+ thing? Okay, so the first question to ask really is, what is the dot? What is it representing? Right? Okay, the dot is representing the start address of the opcode on the same line. In other words, in this case, the period on line 29 is the address of the LDI instruction itself. Are we okay with that concept? The period in a postfix notation or postfix expression refers to the address of the opcode on the same line. Are we good? Is that concept okay? No, it's the LDI instruction. It's the address of the LDI instruction itself. The dot is the address of the LDI instruction, or whatever location is corresponding to that line by the time we get to that line in the assembling process.
So this would be like comparable to putting a label directly above that line and then using that label in that
That is correct.
line. Okay.
Yep. Very good. So Carter has the right idea to explain it, but it's kind of clumsy. It's correct, okay? But if I were to do it like this, then it is correct, okay? So this would have accomplished exactly the same thing. Very good. So, okay, now that we know what that is, why are we adding 6 to it? And why is this accomplishing the same thing that we usually do using an explicit label definition of where they're supposed to return to. Okay, so it's time for Sesame Street and I'll be the count. Okay, because we'll be counting the number of bytes for each line until we get to after the JMPI instruction. We ready? All right. 0, 1, 2, 3, 4, 5, 6. The LDI instruction takes 2 bytes. The JMPI instruction takes 2 bytes. The decrement instruction takes 1 byte. The ST instruction takes 1 byte. 2 plus 1 plus 1 plus 2 is exactly 6. So where we're supposed to return to is exactly 6 bytes away from the LDI instruction itself. And therefore, .6 plus, which really is the postfix notation of .+6, or 6 bytes from the LDI instruction, is exactly where we are supposed to be. All right. So by the time we assemble this program, it will be obvious. Okay, we can actually check to make sure that it's done correctly. Yes.
I just want to confirm the period, when you do that, it's like, because the LDI command is actually going to be stored in a certain part of RAM.
Yes.
So this is telling you like that index where you are in RAM.
+6.
Yeah, like I'm saying, the period.
The period itself, yes. Yep. In other words, if you remember the assemble view of the assembler, remember column W? The dot is referring to column W of that line. Yep.
And if you have a big, long, complicated postfix
Mhm.
expression, and you have a dot somewhere off to the right, does that represent its own location, or does it represent the location of the instruction at the start of the line?
It is still the location of the opcode on the same line.
Okay,
So it's basically the dot refers to the value of column W corresponding to that line. Gotcha. Always.
So you're just using math to replace a label.
That is correct. Yep, I'm basically saying, if I use this pattern, the return address is always 6 bytes away from the LDI instruction. So why would I do something like this? Just to make it look smart, because we know how to do postfix notation, or is there a better reason why I'm doing this? As opposed to having to define an explicit label and then refer to the explicit label.
so you don't have to come up with names for every single label.
Or run into the opportunity of using the wrong label. Because if you are like me, you like to copy and paste, and occasionally forget to change whatever you're pasting, then you can refer to the wrong label. Then your program will be pushing the wrong return address on the stack. So when the subroutine returns, it's going to return to the wrong place. And trust me, those are difficult to debug. Don't ask me why, I know, but I will tell you, just take my words for it. It's difficult to debug. This one, the next time I need to call post-8, copy these 4 lines, slap it somewhere, I'm done. Because the dot is relative to the LDI instruction. So it's all relativistic again.
Makes it modular, so you can use.
Yep, safely. Yep. All right. So what do we do after the post-8 here? After we return, what is on the stack? Is there anything on the stack, that should not be there when I get back from post-8? So let's think about the caller-callee agreement. Okay, the agreement is the caller will push all the arguments, it will push the return address, and then do a JMPI to the subroutine. The subroutine, on the other hand, is free to do whatever it wants with the stack as long as it is below the return address, and then it will consume the return address, meaning it's going to pop the return address from the stack, use it to return back to the caller, which then will end up here. So is there anything else on the stack that really should not be there anymore? The argument, very good. So the argument is still sitting on the stack but we really have no use of the argument anymore because the argument is only needed by the subroutine. The subroutine is done already. So we have to get rid of the argument by simply using increment D in this case. We don't have to copy where register D is pointing to a register because I don't need it back. Because the only entity that needs it is the subroutine, but by the time I get to line 34, the subroutine is done already. So all I need to do is to increment the stack pointer and go like, okay, throw that into the recycle bin, okay? Because I don't need it anymore. All right. So that completes the call to the subroutine with pushing the argument from line 26 to line 34. We are basically done with calling post-inc. So since post-inc is returning a value, is any register being quote unquote special at this point on line 36? According to the caller-callee agreement, what happens to the return value? It's in register A. Very good. So that means register A has the right-hand side. I need to compute the left-hand side. The left-hand side is not a big deal. Okay, we will use the same pattern as last time, except I cannot use register A this time. So I have to use register B, main underscore Y, add BD. So now register B has the address of Y, and then I do a SDBA, and that completes line 15. Are we doing okay so far? Now, if you say I cannot remember everything, that's perfectly okay. Okay, I can send you guys this code as an announcement. And since everything is being recorded, you can basically rerun portions of this lecture if you need to. It's the concept that is important. So you just have to kind of stay with me where the blinky cursor is to make sure that you understand up to that point. If you lose track of some of the earlier stuff, it's not a big deal. Yep.
So for like the exam,
Mhm.
when this kind of like with the dot, is that something that we're going to run into? Will you use multiple methods to say the same thing? Or will it be pretty much standard throughout?
So in the exam, I will use whatever code that will accomplish the same thing. And it is you who has to understand, oh, so this is actually doing that thing that we have been talking about in class, but using a different sequence of instructions. Yep. But there are only so many variations, trust me.
Well, I mean, I guess you could just use an infinite string of numbers to make us compute the math.
There are only so many permutations of these instructions that still work as intended. All right, so we are now done with line 15. We are ready to return. So how do we return? Well, we got the code here already. We are copying whatever the stack pointer points to register B, and then return based on that return address, and we should be done. Really? Are we sure that this is all we need to do? In other words, is the stack pointer still actually pointing to the return address at this point? And I'm referring to line 40. By the time we get to line 40, is the stack pointer pointing to the return address? Or did we actually put something else on the stack earlier? The local variables. The local variables are still on the stack, which means the stack pointer is pointing to the local variable that is occupying the lowest portion of all the local variables. And if I were to do this, we would have been using the value of a local variable, I cannot remember whether it's X or Y, as if it is the return address, which normally would get you to La La Land, not the movie. Okay. Most people do not watch that movie. I only watched like the first 15 minutes of it, so I cannot blame you. So we will be returning to La La Land, which means your program is not going to work the way it's supposed to. So what do we need to do now? Do we still need the local variables at this point? We are done already, right? We are at this point. Okay, we don't need the local variables anymore, so we need to deallocate. So to deallocate something on the stack is just to say, oh, let's increase the stack pointer so that those things are now below the stack pointers, which means they're exposed to the gremlins at this point. I don't care. I don't need those local variables anymore. Now, technically speaking, I still need this line here, because, we are returning a 0 for main. Okay, so technically I still need to put a 0 into register A. So that completes main. And let me take a look at the time. Oh, plenty of time. Now we're gonna look at post main. Okay. So we look at post main. And you can see that main is nothing more than a subroutine. Okay, that's all it is. It's just a subroutine. So post inc is also a subroutine. And I'm going to write the code the way that I usually do, which means I immediately put in the code to return. Because guess what? If I don't do this, I'll forget. Yes.
So using that same logic, would it make sense to, if when you're allocating local variables, also add the deallocate?
Yes.
in
It
the
would make
beginning?
sense. Yep. When you allocate, you also put in the code to deallocate. This way you don't forget. Yep.
If you had like 10 local variables, could you just have inc like 10 times, or is there a better way to do that?
You can use subtract. Subtract would be faster in that case, but if you only have 2 bytes, then decrementing twice is actually faster. Yep. All right, so now we're looking at post inc, and right away we see that we need a local variable. Okay, so that means if I look at the stack, what is it going to look like? The first thing or the highest portion of the stack or this particular frame is the local variable parameter p bar, followed by what? What is right below p bar? P bar is pushed by the caller, and what is the next thing that the caller is supposed to push? The return address, that is correct. Okay, so we have the return address here. So that means, since I only have one local variable in this case, pre is going to be here, and we want to adjust the stack pointer so that it points to the pre. So that means, how do I adjust the stack pointer to allocate for that 1 byte pre? Decrement. Yep. So as what you said, what you guys suggested earlier, we'll also do a matching increment D right away. Well, I also need to use the label definitions. So this way I know where to find what. So post inc underscore pre is going to be defined to be 0, because once I have adjusted the stack pointer, the stack pointer will be pointing straight at the local variable pre. So the local variable pre will be at 0 byte offset from where the stack pointer points. Okay, so that's why the label corresponding to pre is going to be 0. And then we're going to say post inc underscore p bar. Okay, so we can say 2, but I'm just going to say post inc 3 1 plus 2 plus. So it's 2 bytes after that. Well, technically it's 1 plus 1 plus, because the first 1 plus is corresponding to the size of pre, the second 1 plus is corresponding to the size of the return address. So we'll just kind of skip that and just say it's 2 plus. So why do I need the second label? Because I will need to refer to it at some point. Then here and also here. Is that okay? So far? Okay. So now I'm going to write the actual code. The first line is line 6. I have to copy whatever p bar points to the local variable pre. Okay, line 6 of the C code. So as usual, we're going to say LDIA with post inc underscore p var. This is I'm working on the right hand side first. Add AD. So at this point, register A has the address of p bar. All right, so what do I do next? Ultimately, I want the right hand side of line 6, which is the referencing p bar. So what do I do? What do I need to do now? Right now, I just have the address of p bar. What would be the next thing to do? How about just dereference it to get to p bar, right? Okay, so we'll go ahead and do that. So we'll do LDAA. So the A is now PVAR, but not the address. Okay, let's just pause here to figure out what I have just done, okay? To dereference, okay, let me add one more thing, okay? Because I think this will help clarify what I have just done. Okay. Register A ended up with the address of PVAR at the end of line 58. We know that because we have done this in main already, so that's nothing new. On line 59, I'm dereferencing it, okay? So I'm just adding an asterisk in front of the ampersand. Ampersand and asterisk, they cancel out each other because one is the address of, the other one is to follow the address to find out what is at the address. So they kind of cancel out each other. So that's why when these two operators, when the asterisk and the ampersand are next to each other, they kind of annihilate each other. It simplifies to PVAR. So at this point, register A on line 59, register A has the value of the pointer PVAR. Is that okay? All right, yes.
Did you use store?
Nope. Nope, because this is dereferencing and this is a read operation, not a write operation. All right. Is that all we need on the right-hand side? I'll let you guys tell me. What does this look like? And what does this look like? Are they the same? Do I have what I need on the right-hand side of line 6 at this point?
Yes.
Okay. We have PVAR, okay? We have PVAR based on what we document here, but the C code says we need the dereference of PVAR. So we do not, we are close, okay? We're one step closer, but we're not quite there yet. So that means we need to dereference again. But this time when I dereference, I'm just thinking, I'll stash it somewhere else, okay? I'll put it in B. So now B is the reference of PVAR. Is that okay? Because on line 59, register A ends up with PVAR in it, the actual parameter. The value of the parameter is in register A. At the end of line 60, I dereference one more time. So the B is now the dereference of PVAR, which matches what we need on line 6 of the C code. All right. So I know this is difficult to kind of grasp because it's kind of abstract and we have no idea what is what. It's not concrete in any way. But by the time we run this through the assembler and trace the execution, it'll be very clear. Okay, so just kind of bear with me right now until we actually run this code. Yes.
I lost track of one of the earlier lines of code. Can you scroll up just a bit? What happened with the increment? Why did we increment D on line 34 and then do those next 3 lines? What did that correspond to?
Which line again?
34 to 38.
On line 34?
38.
Sorry.
34 to 38.
Okay, so this is for deallocating the argument that's on the stack. And then these two are for deallocating the local variables.
What about the ones in the middle, those 36, 38?
This is to complete the assignment operation on line 15. All right, so getting back to where we left off. So commenting is super important, okay? So if you guys prefer, I can give you a version of this source code with no comments whatsoever, and then you guys can backfill the comment, because I think that is a useful exercise, knowing that you can always get back to the video and find out what it was, but it is useful for you to kind of track it down and then explain in your own words what each line is doing. Okay, let me know if you like that version. I can give you both, okay? The commented version like it is here, and also the one without any comment, so that you can add those comments in your own words. Okay, so we're proceeding. So I think we got everything on the left-hand side, so we just have to do the right-hand side now. So we now have LDI. I cannot use register A, I cannot use register B. Actually, I can use register. Yeah, I cannot use register A or B. I have to use register C here. I'll explain later why that is the case. So we got post ink underscore free add CD and then STC SDC and B, that would complete it. So line 63 is going to finish off what we need to do on line 6 of the C code. And now we move on to line 7. So on line 7, we need to dereference P bar, and this time I don't care about the value. Well, I do, but I'm going to add one to it and then store it back to whatever P bar is pointing to. So based on what we already have in the registers, what it would be the most optimal way to complete the operation that I need to do on line 7. First of all, okay, do we have the content at where P var is pointing to in the register already? Which register has asterisk P bar in it? Register B. Okay, so let's go ahead and just increment B first. But we have to store it back to where P var is pointing to, which means we have a register that is corresponding to just P bar, but not the reference of P bar. Which register would that be? Register A. Okay, so these two lines, line 65 and line 66, is going to complete line 7 in the C code, but only because I planned ahead of time and retain the values of register A here without overwriting it in the next operation. Okay, so tracking the value of the registers and understanding how it relates to the C code is super important. Okay, that really is the key to the final exam, in this class, is to be able to map the code in assembly to the concepts in the C code. That is the key, of this portion of this class. All right, so that is almost done. We only got one more thing to do, which is returning the value free. All right, so do we have a shortcut somewhere here to get to free? Unfortunately, we do not, because we destroyed that value already, because we incremented B. So the quickest way to get back to it is decrement, but that would not correspond to the C code whatsoever. So we are just going to do the long way, which is to retrieve free as a local variable and put it into register A. It's not that bad, okay, because we already know the pattern already at this point. So we're putting the offset of free into register A. We get to the address of free, and then we just need a dereference here to get to the actual value of free, and we're all done. All right. So I'm claiming I'm done with this program. This is supposed to work. And since we got 7 minutes left, you guys are supposed to say, well, I don't think so. Show me this code actually works, right? Prove it. All right, so we're gonna do this. I'm gonna push D to. So this is where Ripple Spider really is handy, because all I need to do is to say where the TTP-ASM file is. So this is called postinc.ttp-asm, because it will copy the code to the source tab, download the code from the RAM file tab, run it in the simulator, and then collect the trace, and then re-upload the trace to the trace raw data, so that the analysis tab will now reflect the actual execution of the program. All right, so let's go back to the browser and check out the assembler and see what's happening. Okay, So if I really just want to check whether the program worked or not, what is the quickest way to check it? I want a 2 in local variable y. I want a 3 in local variable x in main. And that would be the quickest way to kind of quick check in the program, right? So now the question is, where are they? Okay, so we go back to the source code and see if we can figure that out. Okay, let's go back to the source code and try to figure out. Okay, I need to go back to here. All right, so according to the source code, the return address will be using location what in red. It's the very first thing we push on the entire stack. 255, very good. Or FF will be location F E, right? Right one byte below FF, and then Y will be FD. So what we're looking for is some kind of overwrite of X to 3, some kind of overwrite of Y to 2. Those would be the things that we're looking for. Does that make sense? Okay. So now we switch back to the trace analyzer. And I personally really have no idea whether the assembly version of this program worked or not. So I'm just as anxious as you are to try to find out whether the program actually worked or not. So what we can do is we can highlight the entire thing, and then we can just look for certain things. So I think Control G searches. Nope. Okay, I want to trigger the bigger box for search. Find and replace. Control H. There we go. All right. So we want to find out all the updates. Okay. So in this case, now if you don't know how to do this, it's not a big deal. But if you do, it just helps to kind of make the whole thing faster. So I'm using regular expression here to basically look for asterisk F, and I'm interested in the updates to FE and also FD. So I want to use the square bracket to remember EF are both important characters in this case, followed by a single equal sign. And the range that we want to search is column C, and that's all we need to do. So let's go find. Okay, I specified incorrectly because it's DE that I want. So FE, FE are the two locations that I'm interested in, because according to the source code, X is in location FE, Y is in location FD. Okay. So let's find again. Okay, so FE gets 2. So what is FE? FE is X. X got initialized to 2 first. That is correct, because main itself initialized X to 2 initially, but the subroutine would update it to a 3. Okay, so this is all good for at this point. And then the next one is updating FE to 3. So we got the increment. And then we see FD gets 2. That's the Y getting a 2 in main. So I have all the key indicators that the main part of this program is working fine. Okay. But what about the actual completion of the program? Did we complete the program execution correctly? So we scroll down and we want to make sure that we end at a halt instruction as intended. And we also want to make sure that the stack pointer is quote unquote balanced, which means it is returning back to 0, 0. I did not leave any mess behind on the stack. Okay, so let me see. We still got a few seconds. So given those few seconds, what I need to do now is to show you a few things that are important, such as this line here. So according to this line, after this executes, after I update register A, it is supposed to contain the address of P bar. So now you have to draw your own map, okay, on a piece of paper and say, according to what I understand, this location would be local variable Y, this location would be local variable X, this is going to be the argument, or otherwise known as P bar to the subroutine. This is going to be the return address again. This is going to be the pre as a local variable of posting. And so where am I supposed to find P bar? Is it at location FC? Is the address of P bar actually location FC? So going through that exercise to figure out the map first, and then go through this code to verify that your map matches the actual trace left behind by the execution of the program. That is how you study for this stuff. So there's no text per se. I can give you the text, okay, which is really just the callee agreement. Because everything is a result of that. And also the instructions. The instructions are well documented. Well, okay, sort of. They're well documented as the ROM content of TTP. Because that dictates what happens when you execute an instruction. But that is how you study for this class. Are we okay so far with all of this content? All right, so I will give you the assignment and also the lab for today. This one is a little bit different, so just kind of stay with me for a while, for a little bit more. All right, so there are two components to this thing. Okay, I'm just trying to find out where we are. There we go. So the first component is a normal lab activity. This one is due tonight, okay? There are 10 points, but they're basically multiple choice and value stuff that you're used to already. But all of those questions are trying to guide you to get the program written. But you're not expected to have written the entire program by tonight, okay? So that's why the second portion, which allows you to upload the actual program, is going to be due in about a week. So you do have plenty of time, I would say, plenty of time to actually write the code. But tonight's lab has to do with making sure that you understand all the key concepts in order to write the code. There is yep.
Can you make sure to change the due date of the other one?
Yes, I will. But I do want to make sure that you guys know the access code first. So the access code is swap because we're implementing a swap subroutine. I'll see you guys in the lab. Question?
No, comment. I just recently watched a video on YouTube about how to make computer with dominoes.
Dominoes. Yes,
I don't know if you saw that one.
I heard about it.
It's like, yeah, so you basically explain like all the logical stuff.
All the
like,
gates.
all the gates, the AND, or I just thought for for the exam you said no computer stuff, like no things to
Do
choose.
you want to play some dominoes?
Yeah, probably like half an hour I will preparation stuff.
That may not be the best strategy, but
And it's one of the ones.
it's a one shot, yes.
Yeah.
Unless you have a machine to go back and reset all the dominoes, right? You have to make a robot to lay dominoes.
Yeah, but this is requiring mathematics. So. A lot of the exam.
All righty. I'll see all of you. So today is the 20th. That would be the 24th. Oh, did you spill?
Yeah, still a little bit of grease.
Oh, okay. Well, thank you for cleaning up.
Yeah.
Reset.